Imagine holding a grain of sand and trying to comprehend that within its tiny structure lies more atoms than there are stars in our entire galaxy. Now imagine something so massive, so incomprehensibly vast, that if our entire observable universe were shrunk down to the size of that grain of sand, this cosmic monster would still stretch across your entire room. What you're about to discover will fundamentally change how you see the night sky and your place within the grand tapestry of existence. The object we're exploring today is called the Hercules-Corona Borealis Great Wall, and it defies everything we thought we knew about how matter can organize itself on cosmic scales. If you're ready to expand your mind and explore the cutting-edge discoveries that are reshaping our understanding of the universe, make sure to hit that subscribe button and give this video a like. Let's get started. The story of discovering the largest object in the universe begins not with powerful telescopes pointed at distant galaxies, but with some of the most violent and energetic explosions known to science: gamma-ray bursts. These cosmic catastrophes release more energy in a few seconds than our Sun will produce over its entire 10 billion-year lifetime. When massive stars die, or when neutron stars collide, they can create these incredible flashes of gamma radiation that are visible across billions of light years. The Swift Gamma-Ray Burst mission, launched by NASA in 2004, has been detecting these cosmic fireworks for nearly 2 decades. Each burst provides astronomers with a cosmic lighthouse, marking the location of distant galaxies and revealing how matter is distributed throughout the universe. It's like having flashbulbs going off randomly across a darkened stadium, allowing you to map where all the people are sitting. Dr. John Hakila and his colleagues at the College of Charleston were analyzing the distribution of these gamma-ray bursts when they noticed something extraordinary. Instead of being randomly scattered across the sky as expected, the bursts showed a pattern. They seemed to cluster in a specific region of space, forming what appeared to be an enormous structure stretching across more than 10% of the observable universe. The discovery process took years of careful analysis and verification. Unlike seeing a galaxy through a telescope, you can't simply point an instrument at the Hercules-Corona Borealis Great Wall and take a picture. Instead, scientists had to piece together its existence from the distribution of gamma-ray bursts, like archaeologists reconstructing an ancient civilization from scattered pottery fragments. The mathematical analysis revealed something that shouldn't exist according to our current understanding of cosmic structure formation. The principle of cosmological homogeneity suggests that on the largest scales, the universe should appear uniform, with matter distributed relatively evenly. Structures larger than about 1.2 billion light-years should be impossible to form given the age of the universe and the known laws of physics. Yet there was evidence for a structure 8 times larger than this theoretical limit. The Hercules-Corona Borealis Great Wall stretches approximately 10 billion light-years across, making it larger than some estimates of the observable universe's radius when it first became transparent to light. This discovery forced cosmologists to reconsider fundamental assumptions about how the universe evolved from its earliest moments. To understand why this structure is so significant, we need to journey back to the cosmic dark ages, roughly 380,000 years after the Big Bang. Before this time, the universe was filled with hot, ionized plasma that scattered photons in all directions, making space opaque to light. As the universe expanded and cooled, electrons combined with protons to form neutral hydrogen atoms, allowing light to travel freely for the first time. This moment, called recombination, left its signature in the cosmic microwave background radiation that fills all of space. The Planck satellite and other missions have mapped this ancient light in exquisite detail, revealing tiny temperature fluctuations that represent the seeds of all cosmic structure. These fluctuations, smaller than 1 part in 100,000, were the result of quantum fluctuations in the early universe that were stretched to cosmic scales by cosmic inflation. Over hundreds of millions of years, gravity amplified these tiny density variations. Regions that were slightly denser than average attracted more matter, growing into the first stars and galaxies. Meanwhile, regions that were slightly less dense became cosmic voids, vast empty spaces between concentrations of matter. This process of gravitational clustering created the cosmic web we observe today. The cosmic web is one of the most beautiful and fundamental structures in the universe. Like a three-dimensional spider web spanning billions of light-years, it consists of dense filaments of dark matter and ordinary matter connected by nodes where galaxy clusters form. Between these filaments lie enormous voids, some hundreds of millions of light-years across, that contain very little matter. Computer simulations like the Millennium simulation have modeled how this cosmic web evolved over billions of years. These calculations, running on some of the world's most powerful supercomputers, track the gravitational interactions of billions of particles from the early universe to the present day. The results show how small-scale quantum fluctuations grew into the large-scale structure we observe today. These simulations reveal a universe that looks remarkably like a biological neural network, with galaxies clustered along filaments that stretch across cosmic distances. But even the most sophisticated models struggle to explain how a structure as massive as the Hercules-Corona Borealis Great Wall could have formed in the time available since the Big Bang. This is where our story becomes not just about the largest object in the universe, but about the limits of our current understanding of cosmic evolution. The challenge lies in the mathematics of structure formation. Gravity works slowly on cosmic scales, requiring hundreds of millions or even billions of years to pull matter together into large structures. The universe is 13.8 billion years old, which sounds like plenty of time until you consider the vast scales involved. For a structure 10 billion light-years across to form, matter would need to have been moving and clustering on scales that seem impossible given the expansion of space itself. Dr. Lajos Balaz and his team at Konkoly Observatory in Hungary conducted extensive statistical analysis to verify the existence of this cosmic giant. They studied the positions of over 283 gamma-ray bursts in the constellation regions of Hercules and Corona Borealis, looking for patterns that would indicate a coherent large-scale structure rather than random clustering. Their analysis revealed something extraordinary. The probability that this clustering occurred by random chance is less than 1 in 3.8 million. In scientific terms, this represents a detection significance that far exceeds the threshold typically required to claim a discovery. The structure is real, but its existence challenges our fundamental models of how the universe works. To appreciate the true scale of what we're discussing, let's put the Hercules-Corona Borealis Great Wall in cosmic context. The Milky Way galaxy, our home in the universe, spans roughly 100,000 light-years from edge to edge. Our local group of galaxies, including the Milky Way and Andromeda, stretches about 10 million light-years across. The Virgo supercluster, which contains our local group along with thousands of other galaxies, spans approximately 110 million light-years. Even the largest structures previously known to science pale in comparison to this cosmic behemoth. The Sloan Great Wall, discovered in 2003, stretches approximately 1.3 billion light-years across. The huge large quasar group, found in 2013, spans about 4 billion light-years. But the Hercules-Corona Borealis Great Wall dwarfs even these enormous structures, stretching roughly 10 billion light-years from end to end. This scale becomes even more mind-bending when you consider that the observable universe itself is only about 93 billion light-years in diameter. The structure we're discussing spans more than 10% of everything we can possibly observe. It's as if we discovered that a single building occupied 1/10 of an entire continent. The discovery method itself represents a triumph of modern astronomical detective work. Gamma-ray bursts last only seconds or minutes, but they're so energetic they can be detected across most of the observable universe. The Swift satellite, along with ground-based follow-up observations, has cataloged thousands of these cosmic explosions, creating a three-dimensional map of where the most massive stars have died throughout cosmic history. Each gamma-ray burst serves as a cosmic marker, indicating the presence of a galaxy billions of light-years away. By studying the distribution of these markers across the sky and measuring their distances using redshift observations, astronomers can reconstruct the large-scale structure of the universe in ways that weren't possible with earlier technologies. The redshift measurements are particularly crucial for this discovery. When light travels across billions of light-years of expanding space, it gets stretched to longer, redder wavelengths. The amount of redshift tells us both how far away an object is and how long ago we're seeing it. The gamma-ray bursts in the Hercules-Corona Borealis Great Wall show redshifts indicating they occurred when the universe was roughly 2 to 3 billion years old. This timing creates another puzzle for cosmologists. If this structure already existed when the universe was only a quarter of its current age, how did it form so quickly? The early universe was smaller and denser, but it was also more chaotic, with matter and energy distributed differently than today. Understanding how such a massive structure could assemble in the cosmic equivalent of childhood challenges our models of early universe physics. The European Space Agency's Planck mission, which provided the most detailed map ever created of the cosmic microwave background, offers important clues about the early conditions that might have led to such large structures. The temperature fluctuations in this ancient light reveal the initial density variations that served as seeds for all subsequent structure formation. Planck's data shows that the early universe was remarkably smooth, with density variations of only about 1 part in 100,000. These tiny fluctuations have grown over billions of years through gravitational amplification, but the mathematics suggests there hasn't been enough time for them to grow into structures as large as the Hercules-Corona Borealis Great Wall. This discrepancy points to one of the most exciting aspects of this discovery. It might be revealing new physics that we don't yet understand. Perhaps dark matter behaves differently on the largest scales than current models predict. Maybe there are additional forces or fields that influence structure formation in ways we haven't considered. Or possibly our understanding of cosmic inflation needs refinement to explain how larger initial fluctuations could have been created in specific regions. The implications extend beyond pure physics to questions about the fundamental nature of the universe itself. If structures this large can exist, what does that tell us about the cosmic web's ultimate architecture? Are there even larger structures waiting to be discovered? Could the universe be organized on scales so vast that our entire observable cosmos represents just one small piece of an incomprehensibly larger tapestry? These questions connect to some of the deepest mysteries in modern cosmology. Dark matter, which makes up roughly 27% of the universe, provides the gravitational scaffolding that shapes large-scale structure. Dark energy, comprising about 68% of everything, drives the accelerating expansion of space itself. The interplay between these mysterious components determines how structures form and evolve across cosmic time. Computer simulations that include both dark matter and dark energy can reproduce many features of the observed cosmic web, but they struggle with the largest structures like the Hercules-Corona Borealis Great Wall. This suggests our understanding of how these dark components interact might be incomplete, opening the door to new discoveries about the fundamental constituents of reality. The profound implications of the Hercules-Corona Borealis Great Wall extend far beyond its record-breaking size. This cosmic giant is forcing us to reconsider one of the most fundamental principles in cosmology: the idea that the universe looks the same in all directions when viewed on sufficiently large scales. This principle, called isotropy, has been a cornerstone of our understanding since Einstein first applied his theory of general relativity to cosmology over a century ago. If the universe truly is isotropic, then finding a structure that spans 10 billion light-years in one direction, but not in others, presents a serious challenge to our theoretical framework. It's like discovering that what you thought was a perfectly spherical ball actually has an enormous dent on one side. The implications ripple through everything we think we know about cosmic evolution and the fundamental nature of space and time itself. The detection techniques used to identify this structure showcase humanity's incredible ingenuity in exploring the cosmos. Gamma-ray bursts, the cosmic beacons that revealed this giant's existence, were first discovered accidentally in the 1960s by satellites designed to monitor nuclear weapons testing. The Vela satellites, scanning for gamma radiation from atomic bomb tests, kept detecting mysterious flashes from space instead of Earth. It took decades to understand that these gamma-ray bursts represented some of the most energetic events in the universe. When a massive star collapses to form a black hole, or when two neutron stars spiral into each other and merge, the resulting explosion can briefly outshine an entire galaxy. These catastrophic events serve as cosmic lighthouses, visible across billions of light-years, and marking the locations of distant galaxies like streetlights in a vast cosmic city. The Swift gamma-ray burst mission revolutionized our ability to study these cosmic explosions. Within seconds of detecting a gamma-ray burst, Swift can automatically point its X-ray and optical telescopes at the source, capturing the afterglow as it fades over days or weeks. Ground-based telescopes around the world then swing into action, measuring the redshift and determining the precise distance to each burst. This rapid response network has created an unprecedented three-dimensional map of cosmic structure. Each gamma-ray burst adds another point to our understanding of how matter is distributed throughout the universe. When Dr. Hakila and his colleagues analyzed nearly 300 of these cosmic markers, they found them clustering in ways that revealed the outline of something truly extraordinary. The mathematical techniques used to identify this structure draw from fields as diverse as statistics, computer science, and chaos theory. Scientists must distinguish between genuine cosmic structures and random statistical fluctuations, a challenge that requires sophisticated algorithms and careful analysis. The probability calculations that confirmed the reality of the Hercules-Corona Borealis Great Wall involved comparing the observed distribution to millions of computer-generated random distributions. This statistical rigor is essential because human minds are naturally pattern-seeking. We tend to see faces in clouds and conspiracies in coincidences. In astronomy, this tendency can lead to false discoveries if not carefully controlled. The scientific method demands that extraordinary claims be supported by extraordinary evidence, and the existence of the largest structure in the universe certainly qualifies as an extraordinary claim. The verification process involved multiple independent research teams using different analytical methods. Dr. Balazs and his colleagues at Konkoly Observatory approached the problem from a different angle than the original discoverers, yet reached the same conclusion. Something enormous and coherent exists in that region of the universe. This convergence of independent results strengthens confidence in the discovery while highlighting the collaborative nature of modern astronomy. But finding the structure was just the beginning. Understanding what it means for our cosmic worldview requires grappling with some of the deepest questions in physics and philosophy. How do we reconcile the existence of this cosmic giant with our theoretical models? What does its presence tell us about the early universe and the forces that shaped cosmic evolution? One possibility is that the Hercules-Corona Borealis Great Wall represents a relic from cosmic inflation, the brief period of exponential expansion that occurred in the first fraction of a second after the Big Bang. During inflation, quantum fluctuations were stretched to cosmic scales, creating the density variations that later grew into galaxies and larger structures. Perhaps some regions experienced slightly different inflationary dynamics, leading to the formation of super-large structures like this cosmic wall. Another intriguing possibility involves the role of dark matter in structure formation. Current models assume that dark matter particles interact only through gravity, but perhaps there are additional interactions that become important on the largest scales. Theoretical physicists have proposed various exotic forms of dark matter, from axions to sterile neutrinos, each of which might behave differently during structure formation. The discovery also raises questions about the ultimate fate of the universe. As dark energy continues to accelerate cosmic expansion, structures like the Hercules-Corona Borealis Great Wall will be stretched and torn apart over cosmic time. Galaxies within the structure are already moving away from each other as space itself expands. In the far future, this cosmic giant will dissolve into isolated islands of matter separated by ever-growing voids. This cosmic perspective connects your personal existence to the largest scales of reality in profound ways. The atoms in your body were forged in stellar cores and dispersed by supernova explosions that occurred throughout cosmic history. Some of these stellar furnaces might have been located within the Hercules-Corona Borealis Great Wall, making you quite literally connected to the largest structure in the universe. The calcium in your bones, the iron in your blood, the oxygen you breathe, all have cosmic origins that span billions of years and countless light years of space. When you look up at the night sky, you're not just observing distant objects. You're witnessing the cosmic ecosystem that created the very elements of your being. The structure we're discussing tonight represents part of that grand system, a piece of the universe's architecture that has been shaping cosmic evolution since the early epochs of time. Future observations will undoubtedly reveal more about this cosmic colossus and perhaps discover even larger structures. The Vera Rubin Observatory, currently under construction in Chile, will survey the entire visible sky every few nights for 10 years, creating an unprecedented movie of the changing universe. The Nancy Grace Roman Space Telescope will peer deeper into space and farther back in time than ever before, potentially revealing the early formation history of structures like the Hercules-Corona Borealis Great Wall. The James Webb Space Telescope is already revolutionizing our understanding of early cosmic structure formation. Its infrared vision allows it to observe the first galaxies that formed when the universe was less than 1 billion years old. These ancient galaxies provide crucial clues about how matter first assembled into large-scale structures and whether the conditions existed for superstructures like the Great Wall to form so early in cosmic history. The discovery of the Hercules-Corona Borealis Great Wall forces us to confront a humbling truth about our cosmic perspective. For centuries, humans have gradually expanded our understanding of scale, from believing Earth was the center of everything to recognizing our planet as one world among billions in a galaxy that's one among trillions. Each expansion of perspective has revealed new layers of cosmic architecture, and this latest discovery suggests we're still only scratching the surface of reality's true complexity. Consider the intellectual journey that brought us to this moment. Ancient astronomers saw the Milky Way as a mysterious band of light across the night sky. In the early 1900s, Edwin Hubble proved that spiral nebulae were actually distant galaxies, expanding our known universe by a factor of millions. The discovery of cosmic expansion revealed that space itself is growing, carrying galaxies apart like raisins in rising bread dough. Now we're finding that even our expanded view might represent just a tiny fraction of something incomprehensibly larger. The cosmic web that contains the Hercules-Corona Borealis Great Wall operates according to physical laws that seem almost biological in their complexity. Dark matter filaments stretch across hundreds of millions of light years, channeling ordinary matter into the regions where galaxies form. These filaments intersect at massive nodes where galaxy clusters develop, creating a three-dimensional network that resembles neural pathways in a vast cosmic brain. This resemblance to biological systems isn't mere coincidence. Both cosmic structure and biological networks develop through similar processes of growth, competition for resources, and adaptation to changing environments. Galaxies compete for gas to fuel star formation, just as organisms compete for nutrients. Cosmic voids expand and merge like empty spaces in growing tissue. The universe appears to be organized according to principles that operate across an enormous range of scales. The Hercules-Corona Borealis Great Wall represents one of the largest examples of these organizational principles at work. Its 10 billion light-year span encompasses thousands of galaxy clusters, each containing hundreds or thousands of individual galaxies. Within each galaxy, billions of stars provide energy for countless planetary systems. The structure creates a hierarchy of organization that connects quantum particles to cosmic megastructures through an unbroken chain of physical relationships. This hierarchical organization reveals something profound about the nature of complexity in the universe. Simple rules, applied consistently across vast ranges of space and time, can generate structures of breathtaking intricacy and beauty. The same gravitational forces that hold you to Earth's surface also shape the largest structures in the cosmos. The electromagnetic interactions that allow your neurons to communicate also power the stellar furnaces that create heavy elements throughout the universe. Understanding this connection requires grappling with the concept of emergence, where simple components combine to create systems with properties that none of the individual parts possess alone. Water molecules don't individually contain the property of wetness, yet wetness emerges from their collective behavior. Similarly, cosmic structures like the Hercules-Corona Borealis Great Wall possess emergent properties that arise from the gravitational interactions of countless smaller components. The detection of this cosmic giant also highlights humanity's remarkable ability to transcend our biological limitations through technology and cooperation. Your eyes evolved to detect reflected sunlight from nearby objects, yet through telescopes and computer analysis, you can now perceive structures that span distances incomprehensibly larger than your sensory systems were designed to handle. This extension of human perception represents one of our species' greatest achievements. The international collaboration required for modern astronomy exemplifies humanity at its best. The gamma-ray burst data that revealed this structure comes from space missions funded by multiple countries and analyzed by researchers across the globe. Scientists from Hungary, the United States, and other nations work together to understand cosmic phenomena that transcend all earthly boundaries. In studying the largest object in the universe, we demonstrate our ability to think and act on scales that match cosmic reality. This collaborative aspect of discovery connects to deeper questions about consciousness and its role in the universe. We are arrangements of atoms that have become aware of themselves and their cosmic context. Through science, the universe has developed a way to understand its own structure and evolution. Your brain, composed of elements forged in stellar cores billions of years ago, now contemplates structures that span most of the observable cosmos. The philosophical implications extend to questions about purpose and meaning in an unimaginably vast universe. Some might find the scale of the Hercules-Corona Borealis Great Wall diminishing to human significance, but the opposite perspective seems more compelling. The fact that such structures exist and that we can discover and understand them reveals the universe to be far more interesting and complex than random chance alone could create. The mathematical elegance that governs structure formation across cosmic scales suggests underlying principles that connect the smallest and largest phenomena in nature. The same quantum mechanics that describes atomic behavior also explains the initial fluctuations that seeded galaxy formation. General relativity describes both the curvature of space-time around massive objects and the expansion of the universe as a whole. These unified descriptions point toward a deeper coherence in nature's fundamental architecture. Recent developments in our understanding of dark matter and dark energy add new layers to the mystery of large-scale structure formation. The Euclid mission, launched by the European Space Agency in 2023, is mapping the distribution of dark matter across billions of light-years using gravitational lensing. This technique detects how matter bends light from background galaxies, revealing the invisible scaffolding that shapes cosmic structure. Preliminary results from Euclid and other surveys suggest that dark matter might not be distributed as uniformly as previous models predicted. If confirmed, this could help explain how structures as large as the Hercules-Corona Borealis Great Wall could form more quickly than current theories allow. The discovery might be pointing toward new physics that operates on the largest scales, perhaps involving modifications to gravity itself or interactions between dark matter and dark energy that we don't yet understand. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will provide even more detailed maps of cosmic structure across vast volumes of space. Its wide field of view will allow it to survey areas of sky thousands of times larger than Hubble can observe, potentially revealing additional superstructures that challenge our understanding of cosmic architecture. These future discoveries might show that the Hercules-Corona Borealis Great Wall is not unique, but part of an even larger pattern of organization. Perhaps we live in a universe where matter is organized into nested hierarchies of structure, with each level revealing new principles of organization and evolution. The cosmic web might itself be embedded within larger structures that span scales we can barely imagine. The story of the Hercules-Corona Borealis Great Wall teaches us something profound about the nature of scientific discovery itself. Unlike the dramatic moments we often imagine, where a scientist peers through a telescope and immediately recognizes something extraordinary, this discovery emerged gradually from years of painstaking data analysis. The structure was always there, encoded in the positions of gamma-ray bursts across the cosmos, but recognizing its significance required new ways of looking at familiar information. This process mirrors many of the greatest discoveries in astronomy. The cosmic microwave background radiation was first detected as annoying noise in a radio antenna before being recognized as the afterglow of the Big Bang. Dark matter revealed itself through the orbital speeds of stars in galaxies that should have flown apart if only ordinary matter were present. Dark energy announced its existence through observations of distant supernovae that appeared dimmer than expected, indicating that cosmic expansion is accelerating. In each case, the universe was trying to tell us something important, but we needed to develop new tools and perspectives to hear the message. The Hercules-Corona Borealis Great Wall might be delivering a similar message about the fundamental nature of reality, one that we're only beginning to decode. Perhaps it's revealing new aspects of how gravity works on the largest scales, or pointing toward additional forces that shape cosmic evolution. The technological achievement required to detect this structure showcases human ingenuity pushing against the absolute limits of what's physically possible. Gamma-ray bursts last only seconds, yet astronomers must coordinate observations across multiple satellites and ground-based telescopes to capture their afterglows. The precision required is extraordinary. Imagine trying to photograph a firefly that flashes for just 1 second while flying through a forest at night, then tracking its path for weeks afterward. The Swift satellite accomplishes this feat using automated systems that can respond faster than any human operator. Within 15 seconds of detecting a gamma-ray burst, Swift slews its entire spacecraft to point its X-ray and optical telescopes at the source. This rapid response captures the fading afterglow before it becomes too dim to study, providing crucial information about the distance and environment of each burst. Ground-based telescopes around the world participate in this cosmic detective work through carefully coordinated networks. When Swift detects a burst, it immediately transmits the coordinates to observatories across the globe. Robotic telescopes swing into action automatically, beginning observations that might continue for weeks or months as the afterglow fades and evolves. This level of automation and coordination would have seemed like science fiction just decades ago. Today, it represents routine operations in modern astronomy, where discoveries depend on integrating data from multiple instruments operating across the electromagnetic spectrum. The gamma-ray, X-ray, optical, and radio observations of each burst provide complementary information that no single instrument could gather alone. The data analysis techniques used to identify the Hercules-Corona Borealis Great Wall draw from advanced statistical methods developed for fields ranging from particle physics to bioinformatics. Scientists must separate genuine correlations from random noise, a challenge that requires sophisticated algorithms capable of analyzing vast datasets for subtle patterns that human eyes would never notice. Machine learning and artificial intelligence are increasingly important tools in this process. Computer algorithms can analyze the positions and properties of thousands of gamma-ray bursts simultaneously, searching for clustering patterns that might indicate large-scale structures. These same techniques are being applied to survey data from projects like the Sloan Digital Sky Survey and the Dark Energy Survey, potentially revealing additional superstructures throughout the cosmos. The implications of these discoveries extend far beyond pure science to questions about humanity's long-term future. If structures like the Hercules-Corona Borealis Great Wall represent common features of cosmic architecture, they might influence how matter and energy flow throughout the universe over billions of years. Understanding these flows could become crucial as our species eventually expands beyond Earth and begins to interact with cosmic-scale processes. Consider the energy resources available within such a structure. The billions of galaxies contained within the Hercules-Corona Borealis Great Wall represent energy sources that dwarf anything available in our immediate cosmic neighborhood. A truly advanced civilization might eventually learn to harness energy flows on these scales, tapping into the gravitational and electromagnetic processes that shape cosmic evolution itself. This perspective transforms our understanding of what constitutes resources and environment. Just as early humans learned to harness fire, agriculture, and eventually fossil fuels, our distant descendants might learn to work with the fundamental forces that organize matter and energy across cosmic distances. The discovery of the largest structure in the universe opens our imagination to possibilities that extend far beyond current technological capabilities. The educational impact of discoveries like this cannot be overstated. Students learning about the Hercules-Corona Borealis Great Wall are encountering concepts that didn't exist in textbooks when their teachers were students. This rapid expansion of knowledge requires new approaches to science education that emphasize curiosity, critical thinking, and comfort with uncertainty rather than memorization of fixed facts. The discovery also highlights the importance of basic research that might seem to have no immediate practical applications. When scientists first began studying gamma-ray bursts in the 1960s, nobody could have predicted that these cosmic explosions would eventually reveal the largest structure in the universe. The lesson is clear. Supporting fundamental research often leads to discoveries that revolutionize our understanding in ways we couldn't have anticipated. This principle extends to current research programs that might seem esoteric or impractical. Studies of quantum gravity, investigations of extra dimensions, searches for dark matter particles, and explorations of cosmic strings might all contribute to future discoveries that reshape our cosmic perspective as dramatically as the Hercules-Corona Borealis Great Wall is reshaping it today. The international nature of modern astronomy also provides a model for addressing global challenges that require long-term thinking and cooperation. Climate change, pandemic preparedness, and resource management all operate on timescales and spatial scales that demand the same kind of patient, collaborative approach that revealed this cosmic giant. Perhaps learning to think on cosmic scales helps prepare us for the terrestrial challenges we face as a species. The discovery reminds us that we live in an age of cosmic exploration, comparable to the great age of terrestrial exploration that reshaped human civilization centuries ago. Just as maps of Earth gradually filled in blank spaces with new continents and ocean depths, our maps of the universe continue to reveal new realms of existence that challenge our imagination and expand our sense of what's possible. The Hercules-Corona Borealis Great Wall represents one of these new continents of knowledge, a vast territory of cosmic real estate that we're only beginning to explore. Future observations will undoubtedly reveal additional details about its structure, composition, and evolution, each discovery adding to our understanding of how the universe organizes itself on the largest possible scales. The existence of the Hercules-Corona Borealis Great Wall forces us to reconsider one of the most fundamental assumptions in cosmology, that the universe is essentially the same everywhere when viewed on sufficiently large scales. This principle, known as the cosmological principle, has guided our understanding of cosmic evolution for nearly a century. Yet here we have a structure so large that it spans a significant fraction of the observable universe, challenging the very idea that homogeneity emerges at cosmic scales. Think about what this means for our understanding of the Big Bang itself. The standard model of cosmology suggests that the universe began as an extremely hot, dense state and has been expanding and cooling ever since. During the first few 100,000 years, tiny quantum fluctuations grew into the density variations that eventually became galaxies and larger structures. But the mathematics of this process suggests there simply hasn't been enough time for fluctuations to grow into structures as massive as the Great Wall. This timing problem points toward some of the deepest mysteries in modern physics. Perhaps our understanding of how gravity works on cosmic scales needs refinement. Einstein's general relativity has passed every experimental test we've devised, but most of these tests occur in relatively small-scale environments like our solar system. The Hercules-Corona Borealis Great Wall might be revealing new gravitational physics that only becomes apparent when matter organizes across billions of light-years. Alternatively, the structure might be telling us something new about dark matter and dark energy, the mysterious components that make up 95% of the universe. Current models treat dark matter as interacting only through gravity, but perhaps additional interactions become important when vast quantities of dark matter accumulate across cosmic distances. The Great Wall might represent a fossil from an early epoch when these interactions played a larger role in structure formation. The philosophical implications are equally profound. If structures this large can exist, what does that say about the ultimate architecture of reality? We've grown accustomed to thinking of galaxies as islands of matter separated by vast empty spaces, but discoveries like the Hercules-Corona Borealis Great Wall suggest that even these islands might be connected in ways we're only beginning to understand. Consider the information processing required for such organization to emerge. Every galaxy within the Great Wall contains billions of stars, each following gravitational influences that extend across the entire structure. The collective behavior that maintains this cosmic giant's coherence represents a form of information processing on scales that dwarf any computer system humans have ever built. In a very real sense, the universe appears to be computing its own evolution through the gravitational interactions of countless components. This computational perspective opens new ways of thinking about consciousness and intelligence in the cosmos. If the universe can organize matter and energy across 10 billion light-year distances, what other forms of organization might be possible? Could consciousness emerge on cosmic scales through processes we don't yet understand? These questions push beyond current science into the realm of speculation. But they illustrate how discoveries like the Great Wall expand our conception of what's possible. The search for life elsewhere in the universe takes on new dimensions when viewed from this perspective. If matter can organize itself into structures spanning significant fractions of the observable universe, then the emergence of complex chemistry and biology might be more common than we think. The Great Wall contains billions of galaxies, each potentially harboring countless worlds where life could emerge and evolve. Recent discoveries by the James Webb Space Telescope have revealed that complex galaxies formed much earlier in cosmic history than previously expected. Some galaxies observed by JWST appear surprisingly massive and mature for their age, suggesting that the conditions necessary for complexity can arise quickly when sufficient matter accumulates. If similar processes operate throughout structures like the Hercules-Corona Borealis Great Wall, the potential for widespread cosmic complexity becomes enormous. The energy flows within such massive structures boggle the imagination. Galaxies within the Great Wall are connected by streams of gas and dark matter that channel material across hundreds of millions of light years. These flows represent rivers of matter and energy that dwarf anything in our local cosmic neighborhood. Understanding how these flows operate could revolutionize our knowledge of how galaxies form, evolve, and die across cosmic time. Future space missions will undoubtedly reveal additional details about the Great Wall's structure and evolution. The Euclid Space Telescope is already mapping dark matter distribution across vast regions of the universe using gravitational lensing. When massive objects bend light from background sources, they reveal their presence even when they emit no light themselves. This technique is creating three-dimensional maps of cosmic structure that show how matter is really distributed throughout space. The upcoming Vera Rubin Observatory will survey the entire visible sky every few nights for 10 years, creating an unprecedented time-lapse movie of the changing universe. This comprehensive survey might reveal whether the Hercules-Corona Borealis Great Wall is unique or part of a larger pattern of cosmic organization. Perhaps we live in a universe where matter naturally organizes into nested hierarchies of structure, with each level revealing new principles of cosmic architecture. Ground-based gravitational wave detectors like LIGO and Virgo are beginning to detect the space-time ripples created when massive objects collide and merge. As these instruments become more sensitive, they might eventually detect gravitational waves from processes operating on the scales of cosmic structures like the Great Wall. Such observations could provide entirely new ways of studying how the largest structures in the universe evolve and interact. The discovery also highlights how much we still don't know about the cosmos we inhabit. Despite centuries of astronomical progress, we've only recently learned that the universe is dominated by dark matter and dark energy, whose true nature remains mysterious. The accelerating expansion of space was discovered just 25 years ago through observations of distant supernovae. The Hercules-Corona Borealis Great Wall represents another surprise that challenges our existing models and points toward new physics. This ongoing process of discovery connects your personal existence to the cutting edge of human knowledge. The atoms in your body participated in cosmic evolution for billions of years before becoming part of you. Some of those atoms might have been forged in stars located within the Great Wall itself, making you literally connected to the largest known structure in the universe. When you contemplate this cosmic giant, you're using arrangements of matter that have traveled across vast distances and enormous spans of time to participate in this moment of understanding. The collaborative nature of the discovery also demonstrates how modern science transcends traditional boundaries between nations, cultures, and institutions. Researchers from different countries and backgrounds work together to analyze gamma-ray burst data, combining their expertise to reveal something no individual could have found alone. This cooperation provides a model for how humanity might approach other challenges that require global coordination and long-term thinking. The methods used to study the Hercules-Corona Borealis Great Wall reveal something extraordinary about human persistence in the face of cosmic mysteries. Unlike photographing a nearby galaxy where you can point a telescope and capture an image, studying this structure requires piecing together evidence scattered across decades of observations. Each gamma-ray burst provides one tiny piece of a cosmic jigsaw puzzle spanning 10 billion light-years, and scientists must accumulate hundreds of these pieces before the larger pattern becomes visible. This detective work operates on timescales that challenge human patience and institutional memory. The earliest gamma-ray bursts used in the analysis were detected in the 1990s, while the most recent observations continue today. Graduate students who began studying this data as young researchers have become senior scientists, while the evidence for the structure slowly accumulated. The discovery represents not just a triumph of technology, but a testament to the persistence required for cosmic-scale science. The precision required for these measurements pushes against fundamental physical limits. When astronomers measure the redshift of a gamma-ray burst afterglow, they're analyzing light that has traveled for billions of years across expanding space. The wavelength shifts they detect are often smaller than the width of atomic nuclei, yet these tiny measurements reveal distances so vast that expressing them in familiar units becomes almost meaningless. Consider what it means to measure a structure 10 billion light-years across. Light from one end of the Hercules-Corona Borealis Great Wall takes 10 billion years to reach the other end, meaning that different parts of the structure are visible to us as they existed at completely different epochs in cosmic history. We're not seeing the structure as it is now, but as a patchwork of different moments in its evolutionary history, like viewing a person through photographs taken across their entire lifetime simultaneously. This temporal complexity adds layers of difficulty to understanding how such structures form and evolve. Computer simulations that model cosmic structure formation must account not only for the gravitational interactions of dark matter and ordinary matter, but also for the expansion of space itself, the influence of dark energy, and the complex feedback processes that occur when massive stars explode and black holes form within galaxies scattered across the structure. The most sophisticated cosmological simulations require some of the world's most powerful supercomputers running for months to model the evolution of cosmic structure across billions of years. The Millennium Simulation, completed in 2005, tracked over 10 billion particles representing dark matter halos throughout cosmic history. Even this enormous computational effort could only model a region of space much smaller than the Hercules-Corona Borealis Great Wall. Future simulations capable of modeling structures this large will require quantum computers or other revolutionary computational technologies that don't yet exist. The mathematical complexity of tracking gravitational interactions across 10 billion light-years while accounting for relativistic effects, quantum fluctuations, and the expansion of space-time itself pushes beyond the capabilities of classical computation. In a sense, the universe is performing computations through its own evolution that we can barely approximate with our most advanced technology. The discovery also illuminates the remarkable fact that we live during a unique epoch in cosmic history when such structures are visible. The accelerating expansion of space driven by dark energy means that the most distant parts of the Hercules-Corona Borealis Great Wall are already receding from us faster than the speed of light. We can see them now because the light reaching us was emitted billions of years ago when those regions were closer, but no new light from those distant regions will ever reach us. This cosmic perspective transforms our understanding of observation itself. When you look up at the night sky, you're not just seeing distant objects, you're witnessing cosmic history unfolding across different epochs. The nearest stars appear as they were years ago, nearby galaxies as they were millions of years ago, and the most distant regions of structures like the Great Wall as they existed when the universe was fundamentally different from today. Future generations of humans will never see the Hercules-Corona Borealis Great Wall in its entirety because cosmic expansion will carry its most distant regions beyond the observable horizon. We are privileged to live during the brief cosmic moment when this structure spans an observable portion of the universe. In the deep future, only the nearest parts of the Great Wall will remain visible, with the rest lost forever beyond the expanding boundary of observability. This temporal limitation adds urgency to current observational efforts. The cosmic microwave background radiation, the afterglow of the Big Bang itself, is gradually cooling and redshifting toward longer wavelengths as space expands. Eventually, this primordial light will become undetectable, erasing one of our most important sources of information about early cosmic conditions. Similarly, the gamma-ray bursts that revealed the Great Wall's existence will become increasingly difficult to detect as cosmic expansion stretches their radiation to unobservable wavelengths. The discovery process itself reveals deep connections between seemingly unrelated phenomena across cosmic scales. Gamma-ray bursts are created by stellar collapse or neutron star mergers, processes that depend on nuclear physics operating within individual stars. Yet the distribution of these stellar deaths across billions of years reveals patterns in cosmic structure that tell us about dark matter, dark energy, and the fundamental geometry of space-time itself. This interconnectedness exemplifies how modern cosmology reveals the universe to be a unified system where quantum mechanics, stellar evolution, galactic dynamics, and cosmic expansion all influence each other across vast ranges of scale and time. Understanding any one piece of this cosmic puzzle requires grasping how it connects to every other piece, from the smallest quantum fluctuations to the largest structures like the Hercules-Corona Borealis Great Wall. The educational challenge of communicating these discoveries highlights the limitations of human intuition when faced with cosmic scales. Our brains evolved to navigate environments measured in meters and minutes, not megaparsecs and eons. Yet through mathematics, technology, and collaborative effort, we can extend our understanding to encompass phenomena that dwarf everyday experience by factors of billions or trillions. This cognitive expansion represents one of humanity's most remarkable achievements. In less than 4 centuries, we've progressed from thinking Earth was the center of a small universe to recognizing our planet as one world among countless others scattered throughout cosmic structures of unimaginable size. Each expansion of perspective has required abandoning cherished assumptions and embracing new ways of thinking about reality itself. The discovery of the Hercules-Corona Borealis Great Wall continues this tradition of expanding human consciousness through scientific investigation. Like Copernicus realizing that Earth orbits the Sun, or Darwin understanding that species evolve through natural selection, this discovery forces us to revise fundamental assumptions about the nature of cosmic organization and our place within it. The collaborative international effort required for this discovery also provides hope for addressing terrestrial challenges that require similar long-term thinking and cooperation. Climate change, biodiversity loss, and resource depletion all operate on scales that demand the same patient, systematic approach that revealed the largest structure in the universe. Perhaps learning to think cosmically can help us think more wisely about our planetary home. As we contemplate the existence of the Hercules-Corona Borealis Great Wall, we must grapple with a profound realization. We may be living through one of the most remarkable periods in cosmic history for conscious observation. The universe has evolved for 13.8 billion years to reach a moment when matter has organized itself into structures complex enough to contemplate their own existence, yet simple enough that the largest cosmic architectures remain visible and comprehensible. This temporal sweet spot won't last forever. In the far future, accelerating cosmic expansion will stretch space so dramatically that distant galaxies will fade beyond observability. The cosmic microwave background will cool until it becomes undetectable. Even the nearest stars will eventually burn out, leaving behind only black holes and neutron stars in an increasingly cold and empty cosmos. We exist during a brief window when the universe is old enough to have created complexity, but young enough to remain illuminated and interconnected. The Hercules-Corona Borealis Great Wall embodies this cosmic moment perfectly. Its gamma-ray bursts mark the deaths of massive stars that lived fast and died young during an epoch when star formation rates were much higher than today. These stellar explosions scattered heavy elements throughout space, while simultaneously revealing the structure's existence to our telescopes. In a sense, the Great Wall announced itself through the very processes that shape cosmic evolution. This connection between stellar death and cosmic discovery illustrates one of the most beautiful aspects of astronomy. We learn about the universe through the light of dying stars, the afterglow of ancient explosions, and the gravitational echoes of cosmic collisions. Every photon reaching our telescopes carries information about events that occurred millions, billions, or even tens of billions of years ago. We are archaeologists of light, reconstructing cosmic history from electromagnetic fossils scattered across space and time. The technology that revealed the Great Wall's existence represents a triumph of human ingenuity operating at the very limits of physical possibility. Gamma-ray photons carry enormous amounts of energy, yet they arrive at Earth with intensities so faint that detecting them requires instruments capable of counting individual particles. The Swift satellite's gamma-ray detector can register single photons that have traveled across most of the observable universe, carrying messages encoded in their energy and arrival time. This technological sensitivity has opened entirely new ways of studying the cosmos. Before space-based gamma-ray astronomy, we could only observe the universe through the narrow window of optical light and radio waves that penetrate Earth's atmosphere. High-energy astronomy revealed violent processes throughout the cosmos that were previously invisible: black holes devouring matter, neutron stars colliding, and massive stars exploding with energies that briefly outshine entire galaxies. Each new observational window has revolutionized our understanding of cosmic structure and evolution. Radio astronomy revealed quasars and pulsars. X-ray astronomy exposed hot gas surrounding galaxies and flowing along cosmic filaments. Gamma-ray astronomy illuminated the most energetic processes in the universe while simultaneously providing cosmic lighthouses that revealed large-scale structure. Future observations using gravitational waves, neutrinos, and other cosmic messengers will undoubtedly reveal additional layers of cosmic organization. The interdisciplinary nature of understanding the Hercules-Corona Borealis Great Wall showcases how modern science transcends traditional academic boundaries. Nuclear physics explains how massive stars create and disperse heavy elements through supernova explosions. General relativity describes how gravity shapes spacetime around these stellar remnants and throughout cosmic structures. Quantum mechanics governs the initial fluctuations that seeded structure formation and the particle interactions that power stellar cores. Statistical mechanics provides tools for analyzing the distribution of gamma-ray bursts across the sky. Computer science enables the algorithms that process vast datasets to identify subtle patterns. Even psychology and philosophy contribute insights about how human consciousness can comprehend phenomena that operate on scales so far beyond everyday experience. This convergence of knowledge from multiple disciplines reflects a deeper truth about reality itself. The universe operates as an integrated system, where physical processes across all scales influence each other in complex ways. Understanding any cosmic phenomenon requires grasping its connections to the broader network of physical law and natural process that governs everything from quantum fluctuations to galactic superclusters. The discovery also highlights how scientific understanding progresses through the contributions of many individuals working across decades or even centuries. The theoretical framework for understanding cosmic structure formation was developed by scientists like Yakov Zeldovich and James Peebles in the 1960s and 70s. Observational astronomy advanced through the work of thousands of researchers who built and operated the instruments that detected gamma-ray bursts throughout the 1980s, 90s, and beyond. Data analysis techniques evolved through contributions from statisticians, computer scientists, and physicists who developed methods for extracting meaningful patterns from noisy astronomical data. The final recognition of the Hercules-Corona Borealis Great Wall required combining all these advances into a coherent investigation that no individual could have accomplished alone. Science progresses through this collaborative accumulation of knowledge across generations of researchers. The human element in this discovery extends beyond the technical achievements to encompass the emotional and philosophical responses that such revelations inspire. When Dr. Hakila first recognized the pattern in gamma-ray burst distributions, he experienced a moment of cosmic awe that connects him to every human who has ever looked up at the night sky and wondered about our place in the universe. This sense of wonder drives scientific inquiry forward and makes discoveries meaningful beyond their technical details. The same sense of wonder motivates the graduate students who spend years analyzing astronomical data, the engineers who design and build space telescopes, and the taxpayers who fund basic research without knowing what discoveries it might yield. The Hercules-Corona Borealis Great Wall exists partly because humans are capable of finding meaning and purpose in understanding the cosmos, even when that understanding has no immediate practical application. This intrinsic motivation to explore and understand represents one of humanity's most distinctive characteristics. Other species build tools, communicate, and solve problems, but no other known form of life contemplates the structure of the universe or seeks to understand cosmic evolution across billions of years. We are the universe becoming conscious of itself, using arrangements of matter forged in stellar cores to investigate the very processes that created those stellar cores. The discovery of the largest structure in the universe thus becomes a milestone in the ongoing story of cosmic self-awareness. Through our telescopes and theories, our computers and collaborations, the universe has developed the ability to study its own architecture and evolution. The Hercules-Corona Borealis Great Wall exists not just as a physical structure, but as a recognition within cosmic consciousness of its own magnificent complexity. Future generations will undoubtedly discover even larger structures or develop new ways of thinking about cosmic organization that make our current understanding seem primitive. But they will build on the foundation we're establishing today, using our discoveries as stepping stones toward even grander revelations about the nature of reality itself. The story of the Hercules-Corona Borealis Great Wall ultimately becomes a story about time itself and humanity's relationship with cosmic temporality. This structure has existed for most of the universe's history, quietly organizing matter across 10 billion light-years, while stars were born, lived, and died within its vast embrace. Civilizations could rise and fall on countless worlds throughout the Great Wall, entire galactic ecosystems could evolve and transform. Yet the structure itself persists across timescales that dwarf biological and geological processes. When we observe gamma-ray bursts from within this cosmic giant, we're witnessing stellar death throes that occurred when the universe was fundamentally different from today. Some of these explosions happened when the first galaxies were still forming, before heavy elements had been widely dispersed throughout space. Others occurred more recently, in galaxies that had already undergone multiple cycles of star formation and element enrichment. The structure serves as a temporal archive, preserving evidence of stellar evolution across billions of years. This temporal depth reveals something profound about the persistence of cosmic organization. While individual stars and even galaxies are temporary features that form and dissolve across cosmic time, the large-scale structures that contain them appear to be more enduring. The dark matter scaffolding that shapes the Hercules-Corona Borealis Great Wall may have been in place since shortly after the cosmic dark ages ended, providing a stable framework within which countless generations of stars and planets have formed. The implications for life throughout the cosmos become staggering when viewed from this perspective. If the Great Wall has maintained its coherent structure for billions of years, it has provided stable environments where complex chemistry and biology could develop across vast numbers of worlds. The heavy elements necessary for rocky planets in organic chemistry have been steadily accumulating within its galaxies through successive generations of stellar nucleosynthesis. Consider the possibility that some worlds within the Hercules-Corona Borealis Great Wall developed life billions of years before Earth even formed. These hypothetical civilizations would have had access to cosmic resources on scales we can barely imagine. They might have learned to harness energy flows between galaxies, manipulate matter on cosmic scales, or even influence the structure's evolution through technologies that transcend our current understanding of physics. The search for techno-signatures, evidence of advanced technological civilizations, takes on new dimensions when applied to structures like the Great Wall. If intelligence commonly emerges from cosmic evolution, and if it can persist for geological or astronomical timescales, then some of the gamma-ray bursts we observe might actually be artificial signals created by civilizations attempting to communicate across intergalactic distances. This possibility, while speculative, illustrates how discoveries like the Hercules-Corona Borealis Great Wall expand our conception of what's possible in the universe. Traditional SETI efforts focus on detecting radio signals from nearby star systems, but perhaps we should also consider whether cosmic-scale structures might themselves be engineered or modified by sufficiently advanced intelligence. The energy requirements for such projects would be enormous, yet they pale in comparison to the natural energies available within large-scale structures. The gravitational binding energy of the Great Wall exceeds the total energy output of all its constituent stars over their entire lifetimes. A civilization capable of tapping even a tiny fraction of this energy could undertake projects that reshape cosmic evolution itself. These speculations connect to serious discussions among physicists and philosophers about the long-term future of intelligence in the universe. If consciousness represents a natural outcome of cosmic evolution, and if it can eventually transcend its biological origins, then perhaps intelligence will ultimately play a role in shaping cosmic structure formation across the largest scales. The discovery of the Hercules-Corona Borealis Great Wall thus opens our minds to possibilities that stretch far beyond current human experience. We are witnessing not just the largest structure in the known universe, but potentially the arena within which intelligence and consciousness might eventually operate on cosmic scales. The educational implications of this discovery extend far beyond astronomy into fundamental questions about how we prepare future generations for a universe far stranger and more magnificent than we previously imagined. Students learning about the Great Wall today are encountering concepts that challenge traditional boundaries between physics, biology, philosophy, and even theology. How do we teach young people to think on scales that span billions of light years and billions of years? How do we help them develop intuition for cosmic processes that operate according to physical laws they can understand mathematically but never experience directly? These pedagogical challenges require new approaches to education that emphasize imagination, interdisciplinary thinking, and comfort with profound uncertainty. The discovery also raises important questions about how scientific knowledge should be communicated to broader society. The Hercules-Corona Borealis Great Wall represents a triumph of human intellectual achievement that deserves to be celebrated alongside artistic, literary, and musical masterpieces. Yet cosmic discoveries often struggle to capture public attention in societies focused on immediate concerns and rapid information cycles. Perhaps part of the solution lies in recognizing that cosmic discoveries like this one are fundamentally about us. The atoms in our bodies were forged in stellar cores that might have been located within the Great Wall itself. The cosmic processes that organized matter across 10 billion light-years also organized matter into the complex molecular machinery that enables consciousness and curiosity. When you contemplate the Hercules-Corona Borealis Great Wall, you're using neural networks constructed from stellar debris to understand cosmic architecture that spans most of the observable universe. This represents one of the most remarkable achievements in the history of cosmic evolution, matter organizing itself into patterns complex enough to comprehend their own cosmic context. The collaborative international effort required to make this discovery also provides a model for how humanity might address other challenges that require long-term thinking and global cooperation. The same patient, systematic approach that revealed the largest structure in the universe could be applied to understanding and managing Earth's climate, developing sustainable technologies, or exploring space. The discovery timeline itself, spanning decades of observations and years of analysis, demonstrates the value of sustained scientific investigation even when immediate applications aren't apparent. The gamma-ray burst monitoring systems that revealed the Great Wall were originally developed for entirely different purposes, yet they enabled a discovery that transforms our understanding of cosmic architecture. This serendipitous aspect of scientific discovery emphasizes the importance of supporting basic research across multiple disciplines. Today's seemingly impractical investigations might yield tomorrow's revolutionary insights. The universe is far stranger and more wonderful than we currently imagine, and only continued exploration will reveal its deepest secrets. The Hercules-Corona Borealis Great Wall stands as testament to both the magnificence of cosmic organization and the power of human curiosity to unveil that magnificence. In finding the largest object in the universe, we have also found new reasons to marvel at our ability to transcend our biological limitations through science, mathematics, and collaboration. The Great Wall exists not merely as an abstract scientific concept, but as a tangible reality that encompasses countless worlds, countless possibilities for complexity and consciousness to emerge. Every galaxy within its vast embrace represents billions of opportunities for cosmic evolution to experiment with new forms of organization, new ways of converting matter and energy into information and awareness. If this cosmic journey has expanded your sense of wonder about the scales of existence we inhabit, you'll love diving even deeper into how everything connects, from the quantum realm beneath your fingertips to the cosmic horizons beyond our wildest imagination. Check out our exploration of the true scale of the universe, from Earth to the edge of everything, where we'll take you on an even more comprehensive voyage through all the scales of reality that make discoveries like the Hercules-Corona Borealis Great Wall possible. It's a journey that will forever change how you see your place in the cosmic story.